Welcome to topic number 9, making a brick fly, video 2 of 4. In the last video, we gave you a brief introduction to propulsion systems, the theory of momentum change in thrust and change in kinetic energy, and then a brief introduction into piston propeller propulsion systems, where the key takeaway was the advent of propeller efficiency and how that works. In this video, we're going to talk about jet and gas turbine propulsion systems. Again, let's remind you of the questions that we want to be answering over these 4 videos. The first one is how we generate thrust, and we talk about throwing passengers overboard, half jokingly. Then, what are the basics of propulsion, which we covered in the last video, and we gave you an introduction to the measures of efficiency. We'll talk more about efficiency today and in video 4. And then tomorrow, we're going to introduce you to the astronautical propulsion systems. And as we talk about those and the measures of efficiency, I want you to think about what are the differences and similarities between aeronautical and astronautical propulsion systems. So moving on to jet propulsion. In a piston propeller system, we have a working fluid inside our engine and a propelling fluid, and they are 2 separate things. The propeller does not touch the exhaust or the intake to our engine. In a jet engine, we're going to be combining our working and propelling fluids. And they work in a simple squeeze, bang, blow process. We have at the front of the engine our V infinity in. We have a diffuser which slows the flow down so that it enters our compressor at a low enough Mach number that we don't get significant supersonic flow. We do work on the air just like a propeller does, but since we're inside a closed tube, we can do a lot more work. So instead of having a pressure ratio across a propeller of, like, say 1.05 or 1.1, we now have pressure ratios across our compressor of 10, 20, 50 even. We then have a combustor where we add heat to our fluid, just like in a piston prop where we added heat through a spark ignition or diesel compression ignition. We do it here in a more constant way. Then we expand it through a turbine, which we use to drive our compressor, and then accelerate it out our nozzle to get our VJ. Again, the mass flow rate in and the mass flow rate out are not strictly the same, but as you'll see, they're very close to each other. And we'll make the assumption in many cases that they are the same. If we look at pressure across the engine, you can see it goes up as through the diffuser, way up through the compressor. Ideally, it is constant in the burner, and this is what's called a Brayton or Joule cycle. And then it drops through the turbine and again through the nozzle. Temperature goes up as we do work, and we burn, and then comes back down again. But as you see, temperature at the exhaust is higher than temperature in the inlet. And that's very important when we talk about thrust in and around Mach 1. Velocity obviously decreases and increases because we have a constant Mach number in the burner. So as the temperature's up, the velocity goes up, and then tends to do a bit of weird stuff through the turbine and then increases again through the nozzle. And then we, of course, have our forces and our net thrust at the end. Okay. So let's talk about the turbojet engine. It's not the simplest jet engine. That's the ramjet engine because that has no moving parts. Again, it has the diffuser, the compressor, the burner, the turbine, and the nozzle, which we just talked about. It looks something like this. And remember, thrust depends on the disk area, and our disk area is this front end area of our engine. Thrust is mass flow rate times the velocity, just like it was before. But the big thing to remember is now that we're adding much more pressure and much more heat energy to the flow, we can get much higher exit velocities. So our exit velocity is much higher than it is for a propeller system. As such, the flow coming out has significantly more kinetic energy than the flow going in for the same amount of thrust. And that's going to show up when we talk about efficiencies between those 2 propulsion systems. Remember, as specific thrust goes up, i.e. the amount of thrust per mass flow, so the difference in velocity, our efficiency tends to go down. Okay, this is just a chart that shows the loads and how thrust is. And as you'll see, it's interesting where our primary thrust points come from. You think it comes from the nozzle, when in reality, the nozzle creates a drag. Most of our thrust is on the inside of our compressor or of our combustor, and almost about 60% as much on the compressor. But we get a total of about 11,000 pounds of thrust but look at the two different loads. And that's mainly because we spend a lot of effort just keeping the engine together and making sure that everything turns. It's like a wing. We can do the bulk to figure out the gross number, but to figure out stresses, you have to build up your pressure and shear forces. Okay, calculation of thrust for a turbojet isn't that hard. We don't do the buildup across all of these, even with our sophisticated computers. It would be very hard to do across all flight regimes. Remember our simplified equation from our piston propeller system. Now, we also have a difference in pressure because we have a much higher pressure ratio inside our engine. We can have a difference of exhaust pressure and inlet pressure. We have our difference in mass flow rate. We have our mass flow rate of air and of our fuel. So that pressure area creates a force and the mass flow rate creates a force. And this is an important one to remember. And this is especially important when we're dealing with supersonic flight, that this, whether our nozzle is overexpanded, underexpanded, or perfectly expanded, can contribute significantly to the thrust and the efficiency of the engine. Ideally, we would have a perfectly expanded nozzle and PE would equal P infinity. And all of our thrust would be in velocity because it's a better way to get it. It's less lossy. Okay, here's some examples of some real turbojets. These are all single spool early turbojets, and they're quite simple. We have two spool jets with multiple compressors that increase the efficiency of our compression system and of our turbines, but they work essentially the same. The next engine is our turbofan engine. We take our turbojet in the center, and we realize that we have a lot of energy in this flow that normally comes out of our turbine that we accelerate, and a lot of heat. And that's accelerated to a very high velocity, which leads to efficiency losses. It also means there's a lot of heat input that's lost here that we could be using to propel our system. So what we do is we put a slightly bigger turbine or an extra set of turbine in there, connect it to another shaft, and drive a fan. This fan works essentially like a propeller, except for, again, because we're inside a case, we can have higher pressure rises across each stage and total higher pressure rises. So we can get a higher velocity, meaning that we can fly faster and efficiently at higher speeds than we would with the propeller. But essentially, it combines the best of both worlds. It combines the high mass flow rate of a propeller system with the high specific thrust of a jet engine. The turbo prop is essentially the same, but instead of having a fan on the front, we have a propeller that's uncased. Again, we get an even higher mass flow rate, but slightly less specific thrust, and that's the trade. This is an example of a two-spool turbofan. We have a fan at the front, a low pressure compressor or booster, and a high pressure compressor. We have our combustion chamber, and then we have two turbines for each of the shafts, a high pressure turbine, which drives our main high pressure compressor, and our low pressure turbine, which drives our low pressure compressor and fan. This is an example of a Pratt & Whitney engine. General Electric engines are very similar. Rolls-Royce large gas turbine engines tend to be three-spool, where the low pressure, or what they call intermediate pressure compressor, is separate from the fan. More recently, we've had the advent of geared turbofans, where there is a gearbox that separates the speed of this compressor from the fan, but they are driven by a common shaft and a common turbine. Okay, as we're talking about gas turbofan engines, I need to introduce you to bypass ratio. And that's the ratio of the mass flow through the fan versus the mass flow that goes through the core, the combustor of the engine. This is not a ratio of thrust. So a bypass ratio of 10:1 means we have 10 times as much air going through the fan as we do through the core. So the core was 1 kilogram per second, the fan would be 10 kilograms per second. But because of the velocity difference, the ratio of thrust may be completely different. For most of our turbofan engines that you see flying around today, the bypass ratio is in the 5 to 9 range. And that's what we would call a high bypass turbofan. As we get to 9 and above 9, to the 10, the 11, the 12, which is common in some forms of 787 and A350 engine, the Gen X and the Trent 1000 and Trent XWB, and also more common in the LEAP and Pratt & Whitney geared turbofans on the A320neo and the 737 MAX. Those are what we call ultra high bypass ratio engines. As the bypass ratio goes up, the engine gets heavier, the specific thrust goes down, but our TSFCs or efficiencies improve. And you'll typically hear in common parlance TSFC, which we'll talk about in video 4, quoted in pounds per pound per hour, kilograms per kilogram per hour, 1/hour. These are inconsistent units in that we have kilograms force and pounds mass versus kilograms and newtons or slugs and pounds, but it makes our math really easy. We don't have to worry about G, remembering our local gravity. It ends up being 1. And for cruise, for a typical high bypass ratio turbofan, we're in that 0.6 pounds per pound or kilogram per hour range. Okay. Now, I talked briefly about ramjets before. Ramjets have no moving parts. They use just the ram pressure in the air to compress. If we're going supersonic, they also use shock waves to compress. So you don't need a turbine, you don't need a compressor, but you still need a diffuser and an inlet and a nozzle and a compressor. Beyond ramjets is the supersonic combustion ramjet or scramjet. And the only difference between the two is scramjets allow us to have air moving through a compressor at supersonic speeds. And the reason for this is as we go faster and faster, the losses in pressure, total pressure, due to shock waves get bigger and bigger. And if we try to slow the air down below Mach 1, which requires a normal shock, it becomes prohibitive. The efficiency drops off. So while ramjet works beautifully in the Mach 2, Mach 3, Mach 4 range, it doesn't work very well once you get above Mach 5. So if we want hypersonic vehicles, single stage to orbit air breathing systems, we need something that gets rid of that efficiency loss. And one option is the scramjet. Now, what's interesting is it wasn't that long ago we talked about scramjets as this kind of theoretical, maybe workable thing. We know now that scramjets are workable. And part of that's due to the HyperX program, which you can see an illustration of here. And part of that's due to Russian and Australian simplified examples. But we know now that you can produce positive net thrust with a scramjet, and actually military systems are being designed and built today around scramjet engines. If you want to know more about that, ask during our question and answer session. I'll give you a little example of the HyperX program versus the Australian approach, and you'll see which one you think is a better idea. Okay, that brings us to the end of our jet engine section. In video 3, we're going to talk about rocket engines, how they are related similarly to our gas turbine and jet engines, because rockets are effectively a different type of jet engine, but also how they're different. And then finally in video 4, we're going to go and spend a lot of time with our efficiency metrics that we've been alluding to throughout the last 2 videos. So thank you for watching, and I'll see you on the next video.